Well, I think you're the only person here today. Maybe someone will show up late, but I can either, if you have any questions, I'm happy to do that. I can also just like come over there and help you instead of doing it on the board.
It's really just the molecular polarity stuff that we're doing.
At the end of class today? Yeah, absolutely. Okay. Just like some examples and what it means and how that works. Yeah. So, how did you feel about the shapes of things?
I feel good about that.
Okay.
Like the symmetry and that stuff.
Yep. Okay. So when we talk about shapes of molecules, right, he gave you the example of carbon dioxide in class today. So when we look at carbon dioxide and when you look at polar molecules and then polar bonds, you want to break them down into the bonds first and then look at the overall molecule. So we have two sections here. We have the oxygen and carbon bond on the left, and then we have the oxygen and carbon bond on the right. So looking at the purple box, between oxygen and carbon, do we have a difference in electronegativity? What's our trend as we go? Right.
Oh, I see. Oh, yeah. So oxygen electronegative.
Right. Perfect. So, right, we know that electronegativity increases as we go up into the left or up into the right on the periodic table. So oxygen is going to have more electronegativity, which means that it gets this partial negative. That's just the squiggly line. And then if that means that oxygen's more electronegative, it's pulling on the electrons more, it's going to have more negative charge than the carbon, leaving the carbon slightly more positive, right? So overall, those together, neutral. But as we look at it, more of the electrons will spend their time near the oxygen over the carbon. Okay, that's what it means by electronegativity, partial negative, partial positive. So if we have those partial negative and partial positive situations happening, that's what we create as a dipole. And in order to show which which atom is more electronegative, we're going to point towards it in that dipole arrow. So looking at this, we'll point towards the oxygen, saying that the electrons are going to spend time towards that oxygen. Okay. What makes it a dipole is not just an arrow, but by adding a line on the end of that arrow. And I like to think of this as like if you were to draw a circle around it, you get a positive charge, indicating that the more positive side is on the right-hand side of the arrow in this case, and the arrowhead is pointing towards the more electronegative atom. Okay, so that's looking at the carbon for the red or the purple box. For the blue box, is there anything different between that carbon and oxygen? No, right? So it's going to be the same exact thing. That dipole is going to point towards the oxygen, right? The oxygen's still more electronegative. It's still going to pull the electrons more. And then that's going to leave the carbon slightly positive. So this is also going to be, right, slightly positive here, slightly negative here. So overall, the bonds between carbon and oxygen are polar, right? They have differences in electronegativity. The electrons are going to be spending their time on the oxygens. So here in this case, bonds equal polar. However, the molecule, what is the shape of this molecule? It's linear, right? It's just two electron domains. There's no lone pairs. And so the easiest way to think about this is tug of war, right? You have two teams of the oxygens on both sides and your flag is in the center. If you have equal strengths on both sides, tug of warring, right? They're both pulling outwards. Is that center line going to move? No, right? So carbon doesn't move. They cancel each other out. So this is going to be an overall molecule of nonpolar. Right? If I'm being pulled out by my arms, I'm not going to move because I have equal strengths pulling on both sides. So I'm just going to stay no longer polar. Okay, does that make sense for this one.
For the bonds, like, if it was the other way, then that would be non-polar, or like, how does it?
Yep, so we'll do an example. So if we have cyanide, not this one, sorry. This is if we have HCN. All right, let's break this apart into our bonds again. Is there a difference between, let's look at the C and the N first. So is there a difference between electronegativities between carbon and nitrogen? Yes, which one is more electronegative? Yep, nitrogen's more, and you'll have a periodic table on your exam so that you can right, you'll be able to see the trend there as well. Nitrogen is electronegative. So which way is our dipole going to point? It'll point towards the nitrogen, leaving a partial positive at our carbon. Okay. And what about our hydrogen and carbon? Is there any difference in electronegativity there? Yeah, in this case, carbon is going to be a little bit more. We can say that the hydrogen carbon bond are usually non-polar. They're pretty similar in electronegativities. When you have something where you have something that's electronegative, like on your right hand side here, creating a partial positive, in order to try and fix that partial positive, carbon will actually pull those electrons closer. So there is a slight polarity difference here. But in general, if you have a carbon and hydrogen bond, you can call it nonpolar. Okay. So for this case, we'll say that there's no dipole here, right? So this bond here is nonpolar. In reality, we have like a little dipole like this, right? Partial negative, partial positive. In reality, there's just a little bit of a dipole. All right, so for our bonds, we again have a polar bond. And now what happens for our molecule? What's our shape here? Right, your shape is still linear. But do our dipoles cancel out this time? No, now they don't. Right now, if we play the tug of war game, I don't even have a team on the left-hand side, right? I'm just being pulled to the right. So I'm going right. If I'm the center, I'm going to move towards the right. So our molecule is going to be polar as well. Right, I'm outnumbered on the right-hand side. My molecule will be pulled to the right. So the electronegativity and overall polarity of the molecule will be towards the right. Okay, so do you see the difference there between something that's polar because it's unbalanced and then non-polar because it's balanced?
Oh, so like, since hydrogen and carbon, I guess would be less than 0.4 on like the table, do I need to like, will we have a table to do that, and that's how we find if it's non-polar?
Yes, yeah, I think you're usually going to be given values for them. So like carbon would be 2.5, and I think hydrogen's like 2.2, 2.1. So it's right on that cusp of non-polar. Nitrogen is like 2.7 or 2.8, something like that. So then the difference between carbon and nitrogen is greater than is enough to make it a non-polar bond. Or is enough to make it a polar bond, excuse me. So you'd be able to do that math. Or it would be obvious that, right, it's like carbon and fluorine, and you know that that's going to be a difference in electronegativity. Okay, questions there? All right, so now let's look at if we look at BF3, boron trifluoride, what would this Lewis structure look like?
A boron,
Mm-hmm. I will tell you that is it. It just has lone pairs around the fluorine. And what do we remember about boron? Is it happy with 6 electrons? Yes, it is. Yep, that's one of our exceptions. So do you remember the shape for this one?
Trigonal planar.
This is trigonal planar. Okay. So right, just think of a triangle, think of an equilateral triangle. They're all going to be the same here. Do you remember the bond angle between these?
120.
Perfect. Okay. And what about our bonds? Do we have any polar bonds here? And which one is more electronegative? Good. The fluorine is more electronegative. So all of our dipoles are going to point out towards those fluorine molecules. So are bonds polar or non-polar? Bonds are polar. What about our overall molecule?
Well, I guess it depends on the school. How do you see? That's what I'm confused about. Symmetry, I guess.
Yep. So if we were to have an equilateral triangle, right? And now let's play tug of war just with 3 teams now. They're all at equal distance. They're all 120 apart. Are they all equal in strength? Yes. So what does that do?
That makes it symmetrical.
It makes it symmetrical. Perfect. So what's our overall molecule? Perfect, right? Our overall molecule is going to be nonpolar. Right now I'm being pulled like by my feet and then my head. Equilateral triangle, everything's being pulled out at equal length. That center is not going to move at all. So overall our molecule is polar, even though we have polar bonds. Okay, what if I changed this to this?
Yes, it depends on where the dipole is.
Let's put chlorine here instead. Okay. So which way are our dipoles going to face? Good, they'll all be facing away. Chlorine and fluorine are both going to be more electronegative than boron. And again, you would be given values to show that. So do we have polar bonds here? Yep. What about our molecule?
I'd say yeah,
And why would you say yeah?
just because I feel like if they're all polar, and like it's a symmetrical, like it would all spread out evenly.
So, right, if we think about tug of war, let's say fluorines are most electronegative. So it's going to have 3 people pulling on its team. Chlorine is a little bit less electronegative, so now it only has 2 people. So are those 2 people going to be able to match the strength of the 3 people on the other sides? No, right? So the fluorines are going to be pulling out in those directions respectively. So it'll be pulling right this way. But the chlorine's going to try and combat it a little bit, but it's not going to be enough to overpower the fluorines that we have. And so overall, we will have a polar molecule because we no longer have symmetry. It doesn't look the same on all of our bonds. And if we were to look at it, right, strength-wise, the fluorines are going to overpower those chlorines, causing it to be a polar molecule. Does that make sense there? And even if we change this to right, 2 chlorines on the bottom and a fluorine on top, right? Those dipoles are still the same. They all look the same. However, this time our chlorines are gonna cancel out, right? Now that's like if I have my feet spread and they're pulling at my ankles, right? Those would stay those would cancel out because of the vectors, but what happens to that fluorine on top? It's gonna pull it up, right? I'm just gonna go straight up, shoot out the top, right? So our bonds here are still polar. And our molecule is still polar. Like it's not symmetrical all the way around. That help a bit so far? Okay, great. What gets tricky is when we now start switching this into three-dimensional shapes, which becomes your tetrahedral, your trigonal bipyramidal, and your octahedral. So if we had carbon tetrachloride, what is that molecule gonna look like? Mm-hmm. Right, we have carbon and 4 chlorines on the side. What do our dipoles look like? Do we have any?
Those are pretty close to being not polar.
Those are close, but we'll say carbon is 2.5 and chlorine is 3.6. Perfect. Yep, it's going to be going towards the chlorine. So for bond, what shape did I say this was? This is tetrahedral. So our bonds are going to be polar, but our molecule is nonpolar. Perfect. Okay, when you're thinking about the shape of a tetrahedral, in my head, I think of this as a tripod. It's a little bit different than a tripod. But if you think about, right, the feet of your tripod being three of those atoms, like the center where you can extend the top part of it, as the central carbon, and then like where your phone would be as that top carbon. That's how I picture it in my head, just to kind of get a visual representation. The bond angles are slightly different on a tripod than in a tetrahedral, but overall shape pretty similar. So like the connection point between the feet and the top is the central atom, and then right, you can extend to the top for your phone, and then what's touching the ground are your bottom atoms. So if that helps you in terms of like playing tug of war, I use that still to this day. So I find that super helpful. So going off of that, if we have now this molecule, we still have a tetrahedral shape. What are our dipoles doing here? Yep, they're all facing away from the center. So what are our bonds? They're polar. What about our molecule now? It would be polar, right? We've thrown off the symmetry. Something does not look like the others. So we no longer are having canceling out vectors, right? In this case, right, this one would have like a stronger dipole towards the top, right? So if you think of the fluorine as like your phone on the tripod, right, that's going to pull up your molecule would probably go towards the top in this case, for your overall dipole for this. Okay. it's worth noting that a different atom around your central molecule will act the same as a lone pair. Right, so instead of fluorine, if I just gave you this with the lone pair, it would have this same setup that we have here. But now this lone pair throws off the symmetry of the atom, still causing you to have a polar molecule. So even though there's not an atom that creates a dipole, the lone pair throws off the symmetry as well. Does that make sense?
So even if there was like it changes the shape, but I guess it's just if there's a lone pair on the center, then it's always gonna be polar.
Like 95% of the time, yes. I will show you two cases where you'll have a lone pair, but a nonpolar molecule. Okay, so, but most of the time, yes, if there's a lone pair, you can assume that it is going to be polar. In this case, your electron domain geometry is tetrahedral. But your molecular geometry, do you remember what this one is? Yep, this one is trigonal pyramidal. Right, and if you think about that, this is like you extended the feet of the tripod, but not the upward facing pole, right? So you just have that pyramid, you just have the 3 feet forming that pyramid. So a lot of these names like make sense for what they are. If you think about what a trigonal pyramid would be, it looks like that. They don't try to trick you with the names, I promise. Okay. All right, so the fun one I like to ask is what if you had CCl2F2? What would that one look like? Mm-hmm. Yep. So I drew mine like this. Did you draw it differently or same? Okay. So which way is our, or which way are our dipoles gonna go? Yep, still away. So what are our bonds? Polar. What are our molecule?
It would be non-polar because there's 2 for each. No, because they're not cross, or, well, I guess my pictures, I put them on, so I don't know.
Yep, so, right, this is not a planar molecule, right? Whenever we get to 4 electron domains, we now have to think about this 3-dimensionally. So if we think about this tripod, right, we actually have something where the carbon, I will do this. Right, where it looks like this, where the fluorine, chlorine, and carbon, right, the fluorine, carbon, and chlorine, right, that have just a single line, those are all going to be on the plane, so they would fit like straight on the board. But the fluorine on the dash is coming out towards you, and the chlorine, or sorry, the fluorine on the wedge is coming towards you. The chlorine on the dash is going into the plane. Okay, so this is actually, right, a 3-dimensional shape. So if we think about the tripod again, 2 of those feet are chlorine, another one is fluorine, and then the phone's the fluorine. So now this is no longer a symmetrical molecule, right? You could have drawn this as carbon, fluorine, 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 and chlorine. And either one of those is exactly the same. That's what that looks like. You can switch it up and you can rotate the molecule to make it look like that, depending on that 3-dimensional shape you're looking at. So since this is not symmetrical, what is our molecule? Our molecule is going to be polar. Does that make sense why that's not non-polar. Okay. Right, and then if you put, right, 3 and 1, that's the same as if we did 1 and 3, so those are the same there. Alrighty. Continuing on, when you have 5 electron domains, what is our shape?
It's like 5 pyramidal.
So this is going to be trigonal bipyramidal. And again, this looks exactly like how it's named. We could have something in the center, M, and you have X and X, 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 and X going around like this. So 3-dimensionally, you have this pyramid that, right, would be like flat on your bench top. Your X is going to be above the plane on top, and then your other X is going to be below the plane on the bottom. So if you have that trigonal base, this can form a pyramid like this. And then you have the trigonal base here in blue, but this time it's all forming the pyramid towards the bottom. Right, so it's trigonal, as in the base of the pyramid, and then you have 2 of them on the top and the bottom. Questions there? So if you have this, all of the same atom, this would be a nonpolar molecule. When you start removing atoms, right, if you start creating lone pairs, we now would have I'm going to make these Y's on top just so we show the difference. We put a lone pair on our atom. We are going to remove it from the axial positions first. Okay. When we remove it from the axial position, that just changes the strain of the atoms on them, right? All of those bonds have electrons in them. Electrons are negatively charged. So if we're pushing them together, right, they're going to repulse. So this shape here gives us the best, like, stability wise, the lowest energy, which is what our atom wants to be in. So we're going to remove from the axial position first. Does anyone remember what this one is called? Yep, this is seesaw. And if you were to rotate this, do we kind of see the seesaw? Right, we have our bench and then our fulcrum here. So that's where that comes from. This, right, one lone pair, this would be a non-polar, or this would be polar bonds, this would be a polar molecule. That lone pair throws off the symmetry. We no longer have canceling out vectors. Okay. When we have 2 lone pairs, again, we're still removing it from that axial position. Do we remember what this shape was called? Yep, this was T-shaped. And do we see the T? Okay. This would also be a polar molecule. Right, and that's because we have 2 lone pairs on our axial position. That's throwing off the symmetry, right? It doesn't cancel out that triangle that it makes in the center. We just have, like, one of the points being pulled. So that would cause it to be a polar molecule. Yep, and there is cases where we have, or there are cases, excuse me, where we have 3 lone pairs on our atom. In this case, what does our shape now become? This is linear, and what do we know about linear back from 2 electron domains? Was that polar or nonpolar? That was nonpolar. So in this case, now all of our 3 lone pairs are in that axial position. You can think of them as like 3 bonds at the points of your triangle. They're all equal distant away. That's going to cancel out any effects that a lone pair would have on the symmetry. So this linear molecule now becomes nonpolar. So in this case, right, this is our first instance where there's lone pairs on the central atom, but you still have a nonpolar molecule. Questions on that one? Okay. And then our last one is 6 electron domains. Remember what this one was called? Yep, this is octahedral. And in my head, right, if you are doing visuals, I like to think of this as the pyramids of Giza just stacked on top of each other. Right, those all have a square base, and then, right, it's a pyramid. So if we look at it this way, we have a square base this time for our pyramid. And they have one going to the top, and then one going to the bottom. So you have 2 pyramids stacked on each other, but instead of a triangular base, you now have a square base. Okay, I also think of this as like the Sims green dot or Sims thing, for remember that game? I think that's an octahedral. That might have more points, but okay, if we have this molecule here, is this going to be polar or nonpolar?
Maybe nonpolar.
It would be nonpolar. Yep. So the square, right, is all going to be 90 degrees apart from each other. So those are all pointing like at the diagonals of a square. And then you have a linear molecule going up and down. So those would be nonpolar that way. So as long as you have the same atom going all the way around, this would be nonpolar. Okay. If we go to 1 lone pair, this time, instead of removing them from the axial positions, you're going to be moving them. I'm sorry. I lied to you. These are the equatorial positions. They're being removed from for the 5 electron domains because it's around the center like the equator. Those are the equatorial positions. I had my things messed up. For 6 electron domains, we remove from the axial positions first. Right, if you think about the Earth, it rotates on its axis, which is the thing that goes up and down, and an equator around the center. So the triangle is your equator for the trigonal bipyramidal, and your square is the equator for the octahedral. Sorry about that. Happy I caught that now and not later. Okay, so you remove from the axial positions for octahedral. So that's like taking away one of the bottom pyramids, right? Now you just have a pyramid and then, or you have a square base and a pyramid on top. However, this lone pair does squish things a little bit. So It's not a flat pyramid, it's kind of like, would point up a little bit this way. So this does throw off the symmetry, which makes this a nonpolar molecule. Oh, I'm sorry, makes this a polar molecule. Right, which makes sense, even if this was a planar molecule, right, if you're pulling at the diagonals of a square, but then you have the point of the pyramid also having a dipole, that'll pull your whole pyramid up. Do we see why that's polar? Okay, and then the last one we talk about for octahedral is if we have two lone pairs. Again, these are at your axial positions. So what used to be linear is now just two lone pairs. So what do we think that do? What do we think that does for the symmetry?
That's symmetrical.
It would now be symmetrical, right? If you think about linear, we have a linear lone pairs across from each other. It now just creates a square that has dipoles with it. So as long as those atoms are all the same, this would be a nonpolar molecule. So this is the second instance where you have lone pairs on your atom, on your central atom, but a nonpolar molecule. And those are the only two that you need to know that have lone pairs and are nonpolar. Get this guy here. And then this guy here. Anything else, if you see a lone pair, you can confidently say that it's a polar molecule. If you see only one lone pair, it is always polar. If it's two or three, you just need to check to make sure it's not one of these two special cases. All right. Questions further from that? Okay. Does that help answer your questions from earlier today? Yep. Any other questions we want to see today? We feel okay with like drawing Lewis structures and everything. Okay. I think that's really it. I mean, if we can draw a Lewis structure, then you can determine the rest of this. Do you just want to practice a couple?
Yeah, I'm about to have to go.
Yep. Yeah, absolutely. We can just do it. We'll do like 3 examples. So let's do. Let's try those 3. And then I'll tell you that phosphorus has 5 electrons, fluorine has 7. Xenon has 8. Fluorine has 7. And sulfur has 6. Hydrogen has 1. That helps you. And once you have your structure, you can fill in your dipoles. Get the name of the structure, if it's polar or non-polar. Okay, so for PF5, we should get the phosphorus in the center and then 5 fluorines all the way around, giving you 5 electron domains. So you should get trigonal bipyramidal. Is this going to be polar or non-polar?
It would be unfolded.
It would be non-polar. Yep.
Even with those, like, 'cause I know that there's 2 different angles.
Mhm.
It would still be non-polar.
Yes, it would still be non-polar. So the triangle that's at the plane around the equator, those are all going to be 120 degrees away from each other. And then the fluorines are going to be 180 from each other. So that allows it to be symmetrical that way, causing it to be non-polar. And then the angle between like an equatorial and an axial fluorine is the same for all of them as well. Okay, so that would be non-polar, even though it has polar bonds. I forgot to tell you the name, or remind you of the name for the xenon F4. This is square planar, right? So if you think about a pyramid, you're now taking the point of the pyramid off, you're just left with the square base. It sits flat on the ground, so that's square planar. This does have polar bonds, but what is our molecule? Our molecule would also be nonpolar. And then the last one was H2S. Sulfur is just underneath oxygen on the periodic table. So if you think of H2O, we know that that is a bent molecule. Sulfur has the same properties as oxygen because it's in the same group. So it'll have the same structure as H2O. So this is going to be a bent structure. And what do we think this is going to be, polar or non-polar? It will be polar. Yep. Right. It has 4 electron domains. So its electron domain geometry is what? Right. It starts off tetrahedral as its umbrella geometry, but underneath it is the polar, or the bent structure. We have 2 lone pairs. That's like taking like 2 feet of our tripod off. If you take 2 feet of the tripod off, it's gonna fall over. Right? If it falls over, it's polar. So your bent structure will always be polar here. Okay. Any other questions? Feel good? Feel better? Yeah? Okay. All right. If we have any other questions, feel free to ask them. If you're not, by all means, we can end early. I'm not kicking you out either. If you have more questions, feel free to ask them. But I know you only had like 2 days of class because of spring break and stuff, so. Thank you. You all good? Feel good? Great. Thank you so much. Have a great rest of your week.